Okay, everyone. Good morning.
Good morning.
Everybody doing okay? All right. A little cold outside, huh? Bike ride was great. Good. So last time we were talking about oxidations and reductions. We didn't get completely through all of our slides. But what reducing agents do you know of right now? Sodium borohydride. NaBH4. Lithium aluminum hydride, LiAlH4, also abbreviated as LAH. Very good. What will they reduce? Carbonyls, right? To what? To alcohols, right? If I have an aldehyde and I reduce it, what kind of alcohol am I going to get? If I have a ketone, what am I going to get? Secondary, right? If I have a ester, what do I get? I actually get two primaries, right? Because the ester part leaves, and I get the other part from the carbonyl. That's right. So I get primary alcohols. And carboxylic acids, primary. Sodium borohydride is a selective reductant for what functional groups? That's right. So for ketones and aldehydes. Now, if you're real savvy and you look in the literature, you'll find examples of where sodium borohydride reduces other carbonyls when they add additives. Okay? We're not worried about that. What does lithium aluminum hydride reduce? Everything, right? All the carbonyl containing ones. It will reduce a ketone to a secondary alcohol. It will reduce an aldehyde to a primary alcohol. It will reduce a ester to a set of primary alcohols. It'll reduce a carboxylic acid. It is a strong reductant. There is another reducing agent that you all know of that we haven't explicitly talked about in this chapter. But we talked about it in the alkene chapter when we converted alkenes to what? Alkanes. That's exactly right. So when we took an alkene to an alkane, what was the reducing agent? What am I adding across the double bond? No, I'm not adding water. I'm adding hydrogen, and I need a catalyst, right? And I'm just going to write palladium up there. That, too, is a reducing agent, right? It is a reducing agent. And in theory, you can take aldehydes and ketones, and you can reduce them to alcohols using hydrogen and a catalyst. In theory. I've done it before, but it usually requires higher pressure. It doesn't work as well. So catalytic hydrogenation at atmospheric pressure usually, not always, but usually leaves the carbonyl-containing groups alone. Okay? And so that's kind of nice. If we want to just mess with the carbonyl group and leave any alkanes that we have in the molecule alone, what would we use? Sodium borohydride or lithium aluminum hydride. If we want to reduce the alkenes and alkynes and leave the carbonyl groups alone, we'd use catalytic hydrogenation. So you all have already been exposed somewhat to a variety of reductants as we've been talking about them throughout. Okay? Those are the reducing agents you need to commit to memory at this point. Now let's look at some examples that are actually useful. What's the functional group here that's important? That's a ketone. That's exactly right. It also has an aromatic ring, but nothing's going on with the aromatic ring here. Notice they're taking this ketone, sodium borohydride methanol, and they're getting a secondary alcohol. Then they take this molecule, and in a few steps, they can get to ibuprofen. Ibuprofen is a very useful medicine, right? You get out of football practice, you have a headache, you take ibuprofen, or leave, or whatever, but this is ibuprofen. You get done with this class, you got a headache, you might be taking ibuprofen. It is made through a reduction of a ketone using sodium borohydride in methanol solvent, okay? Now, we don't need to worry too much about these steps yet. We'll get to that at a later date. But the key intermediate that they have is a secondary alcohol that they get by simple borohydride reduction. If we look at this particular ketone, what is different about this ketone versus the one that we have up here? It is connected to a ring. What else? It's also in conjugation with a single pi bond, right? So, whereas this is an aromatic ring, this is just what we would call an alpha-beta unsaturated ketone. We'll talk about those a lot more in another chapter. But what you can see is that the sodium borohydride is leaving the alkene alone and simply reducing the ketone to the alcohol, right? And so now we have this alcohol that undergoes 4 steps to get to the odor of musk, muscone. So if you like musky perfumes and colognes, that is the component in there, and it is made through a simple borohydride reduction to get one of the important intermediates that's used to make the rest of the molecule. Okay? So we don't like to kill animals anymore for their scents, so you make them synthetically, right? Muscone, it's a very simple molecule, but it is made through this reduction of a ketone. Okay? So reduction is taking a carbonyl and doing what to it? We're adding hydrogens, right? So the reverse of that process, taking away hydrogens from alcohols to make carbonyl-containing compounds, is oxidation. Okay, and we're going to learn about the variety of oxidizing agents that we can use to actually get those transformations to occur. Okay? So you can imagine, for example, taking a primary alcohol, and you can imagine removing one of the hydrogens on the oxygen of the alcohol and one of these hydrogens on the primary carbon and getting an aldehyde, simply removing 2 hydrogens. However, primary alcohols are tricky because they can be further oxidized to carboxylic acids. Okay? We can take primary alcohols and we can oxidize them to aldehydes and or carboxylic acids. So how many reagents do you think we're going to need to select between an aldehyde and a carboxylic acid? We're going to have at least 2 reagents. Because if Matthew comes in and he goes, you know, I want to take this primary alcohol to a carboxylic acid, he's going to have to select a particular reagent to do that. If Sarah comes in and says, you know, I don't want that carboxylic acid, I need to take that alcohol to an aldehyde, she's going to pick a very different reagent. Okay? So reagent selectivity is going to be important here. Okay? Can anybody think of a common oxidation of a primary alcohol to an aldehyde or carboxylic acid? Have you ever heard about wine going bad? Wine spoiling? Yeah, you can oxidize ethanol to acetic acid. That's what happens when wine spoils. It tastes like vinegar. That's exactly right. So it's taking the primary ethanol all the way to vinegar, which is the acetic acid. That's what happens when you don't cork your wine bottle appropriately and you let it sit for a long period of time. So what in that case would be the oxidant? What would be the oxidizing agent? I think you said it. Oxygen. That's exactly right. To preserve your wine, you want to keep it void of oxygen, right? That's why today we no longer use real corks. We use these synthetic corks that are less permeable to molecular oxygen. Okay? Secondary alcohols, real easy. We only have 1 hydrogen atom on the alcohol carbon to be oxidized, and so you end up with ketones. And tertiary alcohols, no reaction. Why do we not see an oxidation of a tertiary alcohol? There's no hydrogen on that carbon to remove. That's exactly right. Primary alcohols have 2 hydrogens, and both of them can be removed. And so that's why we can either get aldehydes or ketones, or aldehydes or carboxylic acids, excuse me. Secondary alcohols only have 1 hydrogen on that carbon, and that's why we can only get ketones from their oxidation, that we're going to talk about here anyway. And then tertiary alcohols, having no hydrogens on those, or on that carbon of the alcohol, no reaction will occur because there's no hydrogen to remove. It's pretty easy to keep track of, right? So you can see the number of oxidations that are possible is directly related to the number of hydrogens on that carbon. 2 hydrogens, we can do 2 oxidations. 1 hydrogen, we can do a single oxidation. No hydrogens, you can't do oxidation, okay? So let's talk a little bit about the reagents that we're going to use to do these types of oxidation reactions. There are a whole host of oxidants available to us today. But for the purposes of this course, we're going to limit it to just a handful. My goal in this class is not to make you a walking encyclopedia of reagents, believe it or not. Okay? I know at times you're probably thinking I'm making you a walking encyclopedia of reagents, but we're really not. Okay? It turns out that an easy way to oxidize alcohols is to use chromium that's in the +6 oxidation state, chromium metal. Okay? And so there's many reagents that we can use to do that. Chromium trioxide is one. It has chromium in the +6 oxidation state. Sodium dichromate or potassium dichromate, very strong oxidizing agents that are capable of oxidizing alcohols. Another one that is quite common is this organic soluble chromium +6 reagent called PCC. Okay? Pyridinium chlorochromate. Okay? Why is it soluble in organic solvents? What do you think, Paige? Think about it. Why would chromium trioxide not be soluble in organic solvents, but PCC would be? The carbons. That's exactly right. The carbons that we have in the pyridine ring make this salt soluble in dichloromethane. That's exactly right. This has no organic stuff associated with it at all, right? It's insoluble. So you will find chromium trioxide, sodium dichromate, and potassium dichromate. Those oxidizing agents are typically dissolved in a mixture of water and sulfuric acid. Okay? Collectively, I call those reagents Jones reagent. When you have a chromium +6 oxidant in the presence of sulfuric acid and water, I collectively call those Jones reagent. Jones reagent is technically chromium trioxide in a mixture of sulfuric acid and water. Okay? But they all do the same thing, so I collectively call them Jones reagent. So if you hear me say Jones reagent, you need to know that's some sort of chromium in the +6 oxidation state in a mixture of sulfuric acid and water.
Where do you get the Jones part?
I don't remember all the history, but Jones is the one that came up with it many, many years ago as an oxidizing mixture. So it sticks in terms of the nomenclature today. Okay. So, as I mentioned, the oxidation of primary alcohols is the tricky one because we can either get aldehydes or carboxylic acids, right? All right. If we take a primary alcohol and we use PCC as the oxidizing agent, we get an aldehyde. So at that first layer of understanding, you need to know that PCC plus a primary alcohol gives what? An aldehyde. It does that if and only if you're doing the reaction in anhydrous conditions. What do I mean by that? No water. Anhydrous, no water. And that's kind of nice because PCC is soluble in dichloromethane. And dichloromethane, will it dissolve? Will a bunch of water be in dichloromethane? No. It forms two layers with water, right? So primary alcohols plus PCC in a anhydrous environment will give me an aldehyde. I can take that same primary alcohol and I can use a Jones reagent. In this case, they're showing potassium dichromate and sulfuric acid and water. What's the functional group? A carboxylic acid. Here's a little caveat. If I take PCC and I place it in water and do the oxidation, what do you think my product is? It's a carboxylic acid. Water makes all the difference. Both reagents have chromium in the +6 oxidation state. They should do the same oxidation, and they do. Both of them give as the first intermediate an aldehyde. But that aldehyde then reacts with water and gets oxidized again to give you the carboxylic acid. In the top example, in dichloromethane, I don't have any water around to do that next step, which is kind of convenient. Okay? This is actually kind of an important reaction. If you've ever seen chromium solutions, like Jones reagent, it is a brilliant orange-red kind of color. And they used to take that mixture and put it on a solid support. I think it was silica. And at one end, you would have a bag or a balloon, and on one end, you'd have a mouthpiece. And you would blow into it, and the alcohol vapor from your lungs would go through that and change the color of that chromium oxidant, which in the oxidized state is orange, and as it gets reduced by the alcohol, it turns green. And so police officers used to be able to tell whether or not you were inebriated by simply having you blow into a chromium tube, or tube containing chromium salts, and looking at the color change. Okay? It's a breathalyzer test, a breath scan, right? It's a pretty simple way to test it. Can anybody tell me why they don't really use this technology anymore? It's good enough. Good enough to know you shouldn't be driving. It's definitely that good. What do you know about chromium? Chromium's actually pretty cheap. It's toxic. Yeah. Chromium is a toxic substance. It's an environmental hazard. And so, you know, these things were ending up in landfills. And we have better sensors today that are actually electronic, using electrochemical analysis that you can use like a little meter, and you can tell pretty quickly what the exact blood level is. But this was a quick and dirty little experiment that actually worked quite well. It just, chromium's kind of toxic, and you don't want it to end up in the environment. So you used to be able to buy these breath scans, and at one point in the, that's probably the mid to late 80s, I guess, when there was a lot of issues with drunk driving, a lot of bars would actually purchase these and have them to where their customers, before they left, could actually breath scan themselves to see whether or not they needed to call a cab or not. And so it was a convenient way to do it. It's disposable. All you have to do is measure how much of the color here changes, and you were good to go. And it works. You don't need batteries, you know, nothing like that. Works pretty well. This is an example of what that oxidation looks like. So this is what Jones reagent, this is a mixture of chromium trioxide and sulfuric acid and water. Notice that's kind of an orangish red color, right? And as I added absolute ethanol to that Jones reagent, notice what happens to the color. It becomes green, because now the chromium is in a oxidized or reduced form. That's exactly right. It is becoming reduced. So we're going from chromium in the +6 oxidation state to chromium in the +3 oxidation state. Okay, so it's, the alcohol is reducing the chromium, and the chromium is oxidizing the alcohol, right? And so we end up with chromium in the +3 state, which is actually a green color. So we're using inorganic chemistry, because we know that a lot of the transition metals have this wide range of colors that we can access based on their oxidation states, to make these simple little breath scan type analyzers. Now, it turns out the people in my lab really love this reaction, okay, because when we're trying to take an alcohol to a carboxylic acid, we do use Jones reagent. We have a bottle of it in our lab. And why do you think they love this reaction? You can see when it's done. That's exactly right. They simply set up their reaction. They have the Jones reagent in a burette, and they add it dropwise, okay, until the color persists green. The reaction's over. They don't have to do TLCs. They don't have to go run a GC. They don't have to go run a quick NMR. They just wait for the color to change and become green. And when that happens, reaction's over, and they're good to go. This reaction, can anybody kind of give me an idea about how fast you think it might be? That's right. Also, if you can put it in a breath scan where you could just blow through it and tell pretty quickly what your blood alcohol content is, it's got to be pretty fast. You don't want somebody blowing a tube and then wait an hour and a half, right? That's just not going to be very efficient. So this reaction is essentially instantaneous. As soon as it drips into the alcohol solution, oxidation occurs and you see the color change. Okay? Now, there are other oxidants that you need to know about, and you have these in your body right now. You have alcohol dehydrogenase in your liver. Okay? Alcohol dehydrogenase is an oxidizing enzyme. That's what it does. It takes an alcohol and it removes hydrogens from it. That's what the name means. Okay? And so in biologically speaking, if we go to the bar and we have a drink of ethanol, okay, I have a shot of my favorite Jack Daniels, and my liver's going to start working on this. And the alcohol dehydrogenase is going to oxidize that first to the aldehyde, which is acetaldehyde. Okay? And then it gets oxidized to acetic acid or acetate at blood pH. Okay? So I'm getting acidic components in my bloodstream. Okay? Acetaldehyde is what's responsible for the hangover. It's what dehydrates you. Okay? It's not the acetate itself. So if you drink alcohol in excess really quickly, you build up a concentration of acetaldehyde, which causes the toxic effects. Okay? Acetaldehyde is toxic. You can build up too much of that, and it will kill you. I mean, you've probably heard of college kids binge drinking and dying from overindulgence, right? It happens. And it happens because they build up a large concentration of acetaldehyde, which then gets oxidized to acetic acid, which then lowers their blood pH, which then kills them. Your blood pH has to be within a very narrow range, right? So all that stuff you learned in Gen Chem about buffers, it's going to come back to haunt you when you get into biochem, because it's very, very important to have pH of biological systems very well regulated, okay? If, however, you happen to ingest methanol, wood alcohol, we know that that'll kill you, right? And the reason is because this enzyme, alcohol dehydrogenase, will not distinguish very well between ethanol and methanol. It'll work on both of them, okay? And so the methanol first gets oxidized to formaldehyde. And formaldehyde is used to embalm. And what do we embalm? Dead things, all right? So not only are you killing yourself, you're giving yourself your own embalming fluid. Yeah, I guess that's one positive output. Which can further get oxidized to formic acid. What's formic acid? Ant bites. That's exactly right. It will lower your blood pH really quick, and it'll kill you, okay? So if you ingest a little bit, you get a lot of formaldehyde, you go blind. Believe it or not, you're fortunate, because if you drank just a little bit more, you're dead, okay? So methanol to formaldehyde to formic acid. This is why distilling your own alcohol at home is a bad idea, unless you really know how to do it well, because in the process of making whiskey, for example, you get both methanol and ethanol in the process. Not much methanol is made, but there is some, and you have to distill that out first. So you want to make sure that whoever you're buying your hooch from knows how to make it right, because you can end up going blind, okay? At the beginning of this chapter, we talked about the fact that we can use nucleophiles to react with carbonyl compounds, right? And that's so far at this point, what has our nucleophile been? It's been hydride. But is that the only nucleophile that we can add to a carbonyl? No. Hydride allows us to get reductions, right? But we can think of other reagents that will also add to these carbonyl compounds and give us alcohols. And these are the organometallic compounds, or the organometallic reagents. What do I mean by organometallic? What did you get from your reading? What's an organometallic compound? Pardon? Metals with carbons. That's exactly right. And it's very, very important. An organometallic compound has to have, by definition, at least one carbon-metal bond. You can have a metal and an organic material that are linked together that are not organometallic. Okay? An organometallic compound must have a carbon-metal bond. Okay? And we're going to talk about those. Which reagent would be best to do this transformation? What's the transformation? It is an oxidation of a what kind of alcohols? To ketones. There are two up there that you should eliminate right off the bat. What are they? B? Right off the bat, I would eliminate A and D. Why would I eliminate A and D? They don't make sense. Why don't they make sense, Gabby? They are not oxidizing agents. Very good. Potassium hydroxide is a base. H3O plus is an acid. Don't make any sense. So it can either be B or C. C's what? C is a reducing agent. So that's not what we're doing, right? So the answer is B, right? That is potassium dichromate in sulfuric acid and water. All right, so it's a Jones reagent. What? Well, that's what the inverted lectures are for. Yeah, those are team tests. That's right. Small teams, but team tests nonetheless. Okay. What other reagent would work here? Do I need water? PCC would work just fine. And actually, PCC, even if it's in water, will only take a secondary alcohol to a ketone. That's all it can do because it only has one hydrogen to be oxidized. PCC will always give a ketone regardless of what medium it's in if it's a secondary alcohol. Okay? Why did they choose potassium dichromate and not put PCC up here? PCC is expensive compared to potassium dichromate. So unless you want to do the selective oxidation of a primary alcohol to an aldehyde, avoid PCC. It'll work, but it's going to cost your boss a lot more money. Okay? Which reagent will best accomplish this transformation? So we're oxidizing, but we're taking what type of alcohol? Primary. So when we see a primary alcohol, we need to stop and ask ourselves, what's the product? What are we getting here? An aldehyde or a carboxylic acid? We're getting an aldehyde. So what's the answer going to be? It'll be D, PCC. That's right. Now, the one that you should have eliminated without any discussion would have been A, right? Because it's a reducing agent. But B, C, and D are all oxidizing agents. Okay, C, potassium permanganate is an oxidizing agent, but it will over-oxidize alcohols to carboxylic acids, just like potassium dichromate will. Okay? So in this case, you're looking for PCC because we want to do the selective oxidation of a primary alcohol. How about this transformation? What are we doing? We are doing a reduction of what to what? Okay, and what are we leaving alone? We're leaving an ester alone, and what else are we leaving alone? The alkene. So we need a reducing agent that will only reduce a ketone and leave an ester and an alkene alone. What would that reagent be? That would be A, sodium borohydride. That's right. What would happen if we used B? We would reduce the alkene. That's exactly right. What would happen if we used reducing agent D? I would reduce the ketone to the secondary alcohol. What else would I reduce? The ester to a primary alcohol here, right? And then this would leave as methanol. That's right. So yeah, you'd end up with another one. What about the double bond? Lithium aluminum hydride will leave the double bond alone in this case. Okay? So what about sodium hydride? Why doesn't it make any sense? You got to justify your... Okay, we didn't talk about it. But we've talked about sodium hydride before, haven't we? We've used sodium hydride in some reactions before. What did we use it as? It is an H minus, but I thought we talked about sodium borehydride being like H minus too, right? We did. Ah, that's right. We used it as a base. Sodium hydride is not a hydride nucleophile. Okay? It is a true salt, and it will not form hydride in solution to do the chemistry like you think it might. Sodium hydride simply functions as a base. Okay? Do we have any acidic hydrogens there that would need to be utilized in the transformation? No. We are reducing a ketone to an alcohol and leaving the rest of the molecule alone. We need a selective reducing agent, and that's going to be sodium borohydride. All right. We are not limited to the hydride nucleophiles in these reactions. Okay? We have other nucleophiles that we can use, and you need to know these by name. Grignard reagents, alkyl lithiums, and alkanides. And we've talked about the alkanides before. Okay? And we've talked about the alkyl lithiums a little bit before. What's so special about a Grignard reagent? Why does it have a separate name as opposed to the alkyl lithiums and the alkanides? Because it's just a methyl group? Well, the alkyl lithium there just has a methyl group too. What's different about them? It has magnesium. All Grignard reagents will have a carbon-magnesium bond. Okay? They will all have a carbon-magnesium bond, and they're named after Victor Grignard, who discovered them and won a Nobel Prize for them. He was from Harvard many, many years. Well, it's been probably about a century now. Okay? But they're very, very important. And you all will actually make a Grignard reagent in lab this semester. Okay? You are not going to make an alkyl lithium. Can anybody tell me why? Alkyl lithiums are very difficult to handle, potentially flammable, and when exposed to air. Do a Google on YouTube for the reaction of tert-butyl lithium, which is an alkyl lithium. You can take it in a syringe and you can shoot it across the room and a green flame comes out. It's like a flamethrower. Lithium, it's not because of an alkyl lithium, but it's...
Don't you use it in like a air bag?
You can use it in an inert atmosphere bag. Yeah, or there's ways to handle it. For those of you who don't know, a couple of years ago, there was a big incident at, I believe it was at UCLA, one of the California schools. There was a young lady who was either a PhD student or a postdoc, I can't remember which now. She died because she was working with alkyl lithiums. She was working with tert-butyl lithium, which is highly pyrophoric. What do I mean by pyrophoric? Spontaneously flammable on exposure to air. And she was working with way more than she should have been. She was not properly trained. This stuff got spilled on her jacket, and it went up in flames immediately. She did not survive. Her advisor has been sued. The school has been sued. And that is one reason why we aren't going to have you all work with alkyl lithiums. It takes a special level of training to work with them. However, Grignard reagents, you wouldn't want to get them on you, but they're not going to spontaneously burst into flames. Okay? So a lot safer. Now, pardon?
What's the advantage of using an alkyl lithium over Grignard?
Stronger base. So we quite frequently, and they're stronger nucleophiles. So we typically use them when a Grignard just isn't strong enough to do the job.
The alkyl lithium, so when it comes in contact with like air or something, it bursts. Like, what makes it burst into flames spontaneously?
Well, when it reacts with the moisture and the oxygen in the air, it gets converted into a hydrocarbon, which ultimately, at the high temperature, is flammable. I mean, and it's a very exothermic reaction, and so the organic stuff catches on fire. We don't use a vacuum, but we use a special set of techniques, transfers, where we're doing it under inert atmosphere. Usually in our lab, we either use argon or nitrogen gas, and we'll use syringes to pull it in so that it's never exposed to. It's something that takes some finesse. You have to know what you're doing. You can't just go in day one and be ready to work with it. It can be very hazardous. These things behave as if they are carbanions, C-. Methyl Grignard acts like CH3-. Why do I have it in quotes? It's not really that, but that's how it behaves. Okay? The methyl lithium also behaves like CH3-. And the alkanide behaves like an alkyne anion minus. And carbon with a negative charge is a pretty darn good nucleophile. And so we can imagine these nucleophiles attacking the carbonyl compound, breaking that weak pi bond to give us a tetrahedral intermediate, which then, after the end of the reaction, when we dump water on it, we get the alcohol. Okay? So if I take an aldehyde and I treat it with, let's say, methyl Grignard, what will my product be? Help me out, Gabby. So I'm going to take acetaldehyde, and I'm going to react that with methyl magnesium bromide, which is a Grignard. What's my product going to be after I work it up? All right, so I can think of this as CH3-. I can think of it like that. It's not real, but I can think of it. That's how it's going to behave. What's this going to do? What's it going to attack? Carbon to the carbonyl. I'm going to break what? The weak pi bond. That's right. And so I end up with, just drawing all my atoms here. And then Gabby will throw that on water to work it up, and we end up with what product? I end up with a secondary alcohol. That's exactly right. So a organometallic reagent plus an aldehyde gives me a secondary alcohol. What do you think a organometallic reagent plus a ketone will give me? Tertiary alcohol. Okay? And we'll talk about some other alcohols that we can get as well. We are not limited to the hydrogen nucleophiles. At this point, you guys have learned how to make a lot of stuff. Just in this lecture today, you've learned how to take an alcohol to an aldehyde. You've learned how to take an alcohol to a carboxylic acid. You've learned how to take an alcohol to a ketone. And now you're learning how to take an aldehyde to an alcohol. You're learning how to take a ketone to an alcohol using other types of reagents. What's really, really important about this particular reaction, though, with the organometallic reagents? What's so important about that? What do you think, Karina? I add a carbon. I'm making a what kind of bond? I am making a sigma bond to what? Between two carbons. There are really only about 5 or 6 ways in general to make a carbon-carbon bond. There are books that are this thick on how to make alcohols, how to make amines, how to make things that have heteroatoms. But the ways in which we can make carbon-carbon bonds is actually small. But it's so important. Why is it so important? That's how I can take smaller molecules that oil gives me and convert them into larger molecules that I want. That's how you guys in polymers take small molecules and make huge molecules, is by making carbon-carbon bonds. Okay? This is one way to make carbon-carbon bonds. You will know by the end of this class, in general, not all the specifics, But in general, you'll know about 95% of everything that I know about making carbon-carbon bonds. The specifics are the other 5%, okay? So this is one of those reactions that is so important because there's so few ways to make carbon-carbon bonds in general, okay? And so organometallic reagents plus carbonyl-containing compounds allows us to do this, okay? Now, the reason that this behaves the way that it does, if you look at the metals and you look at their electronegativity, you find that carbon is actually more electronegative than the metal, meaning that carbon is going to pull those electrons in that carbon-metal bond closer to itself, right? And so that gives the carbon a partial negative charge. That's why I can think of methyl Grignard as CH3-, because the methyl group is pulling the electrons from magnesium to itself, okay? And so what we find are that Grignard reagents and alkyl lithiums actually have a covalent bond. They're not salts, but it's highly polarized, okay? If the metal is a sodium or potassium, it's truly an ionic bond. So that sodium alkanide that we looked at on the previous slide, it was actually sodium plus C, HC minus. I mean, that's what it was. It was an actual ionic compound. These are polar covalent. And then if you have organometallics that have lead, tin, or mercury associated with them, those are truly covalent bonds. They're not polarized very much. We've talked about organometallics before when we talked about the oxymercuration-demercuration sequence, right? Because that carbon-mercury bond was in that, after the intermediate from that first step, right? We made an organometallic reagent. You could actually use that and do some other chemistry with it with carbonyls if you wanted to, okay? But we typically don't like doing chemistry with mercury and lead and tin because of its toxicity, okay? Now, the preparation of these reagents is really, really easy on paper. You all, about a third of you will not be able to get your Grignard reagent to form. And why? I'm going to predict. And if every one of you get your Grignard reagent to work in the lab, I'll have us a pizza party. I'm willing to bet on it. Okay? First time. First time. I'll buy whatever you want. Because it all comes down to how careful you are with your technique. If you are really good with your technique and you're meticulous, it'll work like a shot. If you're a little sloppy, it'll prove it to you. Okay? It's the way it'll work. So, making organolithium reagents is very easy. You take something like diethyl ether that has no water around because lithium reacts explosively with water. You add lithium metal, and then you drip in an alkyl halide. And the alkyl halide can either be a chloride, a bromide, or an iodide. And what you get out of that reaction is an alkyl lithium plus a lithium salt. Okay? How do I know the reaction's over? I have a precipitate of the lithium salt. That's exactly right. And you make the alkyl lithium. Now, it turns out that the iodides are more reactive than the bromides, more reactive than the chlorides, and that follows the trend that we see as we go down a periodic table, right? It turns out that if you make alkyl lithiums this way, you have to use them immediately because they're unstable. The alkyl lithium is a strong base. Some people call them super bases because the alkyl lithium actually has a pK of around 50. It's about as high as you can get. That's why I was saying we use them as strong bases. And when they sit around in ether, they're so strong that they actually promote an elimination reaction to give an alkene plus an alkane plus a lithium salt of an alkoxide. That's not what you want. So if you prepare them like this, you have to prepare them and use them immediately. This reaction takes a little while, okay, to go, but it still happens. It's an E2 reaction. Why is it an E2 reaction? Pardon? Okay. I've got the base attacking the acid, right? I've got the hydrogen carbon bond electrons coming here to form the alkene, and this is leaving as a leaving group, right? That is exactly an E2 elimination. Now, you can buy some alkyl lithium reagents, and they'll ship them to you, but they're not an ether. What solvent do you think alkyl lithiums might be more stable in? Pardon? An organic solvent that is purely hydrocarbon. That's right. So something like pentane, hexane. You can even buy them sometimes in some higher order like decane, different things like that. Things that only have carbon-hydrogen bonds are fairly inert. But if you make them in ethers, you have to be pretty careful. Okay? The Grignard reagents are the safest to work with. Okay? 1900, won the Nobel Prize in 1912, so just a little over 100 years ago. And so they bear his name. You take an alkyl halide, it can be an alkyl bromide, an alkyl chloride, or an alkyl iodide. The same reactivity order is observed. You put it in diethyl ether that's anhydrous, and you add magnesium metal, and you will form a Grignard reagent. Okay? If you have any water around, it kills this reaction. That's going to be the thing that kills some of you guys. You guys will wash your glassware or get some sweat in it, and then your reaction dies. But if you're careful and you use dried glassware and you're very meticulous about keeping the water out, you'll be able to get the reaction to go. How will you know when this reaction is over? The alkyl lithium we know by looking at a precipitate. How about here? All the magnesium's gone. Or you start to see the magnesium, it looks like it's dissolving as the reaction occurs, okay? And you get the magnesium insertion between the carbon-halogen bond. If you're wondering how in the world that happens, we can talk about that later. It's actually a complicated process that I'm not going to hold you responsible for, okay? But it's a free radical process that occurs on the surface of the magnesium. And basically what it does is it inserts the magnesium between the carbon-halogen bond. And that halogen sticks around, no salt to fall out of solution. So it's a pretty well-behaved reaction. Okay? So they're pretty easy to make. In the last bit that we've got here, let's look at a couple of examples. So let's see. Let's say we are going to take how could I do that transformation? Have I taught you how to take an alkyl bromide and convert it into a ketone? Not a bit. That's exactly right. We've got to start thinking backwards, right? We know we can make a ketone from a primary alcohol by oxidation. So thinking backwards, I know I need that particular alcohol. Do I have that as my starting material? No, but how can I make an alcohol? I can make that from an aldehyde and a Grignard reagent. That's a magnesium, I'm sorry. So if I have that plus that aldehyde, I can get that alcohol. And from that alcohol, I can get that ketone. So now tell me the forward reaction. What do I need to do? What's the first step I need to do here? I need to make the Grignard. What's the second step? I've got the Grignard. Now what do I do with it? Think about how we thought about it in reverse. What do I need now? I need the aldehyde, right? That gives me that. Now what do I do? What reagent do I need to go from here to here? I need to remove hydrogen, so it's what kind of reaction? It's oxidation. What oxidant would I use here? I'd use a chromium reagent. I would just use Jones reagent. I have not taught you how to go directly from here to here in one step. But we got to start thinking backwards. You have all the tools in your toolbox to do this kind of stuff. It's going to take practice. Some of you will be frustrated. Relax. Enjoy the ride. Learn how to do it. It's problem solving. Okay? If you like working crossword puzzles, if you like working those types of things, you're going to love this. Okay? How to get to a product with given what you're given is kind of exciting and challenging. I will see you. I'd say we don't have class Monday, right? So enjoy Mardi Gras a little bit and study some, and I'll see you on Wednesday.